All right, guys, so our first unit that we're going to dive into this year has to do with temperature and heat and change of phase and stuff like that. Today we're going to start with just some general conceptual stuff about atomic theory and temperature. So let's start off with the atomic theory of matter. This was a concept that was put forth way back in ancient Greek times, specifically by a man by the name of Democritus, who also gave us the concept of democracy, which is kind of cool. He was a pretty smart guy. You know, he came up with some general ideas. And here was the idea. Democritus was thinking, listen, what if I took a hunk of gold and I chopped it in half, I'd have 2 hunks of gold, right? And I chopped those in half, I'd have 4. And I chopped those, I'd have 8. And he was thinking, what if I chop them smaller and smaller and smaller and smaller, would there be a point where I would have the smallest piece that is gold, like a little thing that would be a little nugget of gold that I couldn't break any further? Or is matter made up of stuff that you can just continue chopping up forever? And back then, you know, they didn't know, but it was a general, like, think about it, you know, theoretically, that's an interesting concept. Can stuff be broken down infinitely, or will you get to a point where you get the smallest piece of stuff that is that stuff? And he thought that was the case. He thought that was what reality was, and he gave it a name. He called it atomos, which means that which cannot be divided. And that's what we call atoms today. Atoms are the smallest piece of stuff that still is that stuff and can't be divided further, right? Does that make sense? So Democritus is the guy that came up with the idea, and that's the general concept behind what we call atoms. An atom being that which is no longer divisible. We now know that you can divide atoms into smaller things, but those things won't be the original thing. Does that make any sense? Like if I have an atom of gold, that's the smallest piece of gold that there is. And if I break it further, I'm looking at protons and neutrons and electrons. I'm not looking at gold anymore. Yeah? Okay. Now, this was, again, it was a theory that Democritus came up with way back, you know, in the time of Christ and, you know, way back then. And we didn't have any way of really testing it. So you had people that believed in the atomic theory and people that did not believe in atomic theory for a long time. But there started to be more and more evidence in the 17th century and 18th century as scientists began investigating the world a little bit more closely. First piece of evidence that the atomic theory held true was this thing called the law of definite proportions. And this was when chemistry was really, really big. You had these chemists breaking apart all kinds of different molecules and stuff and breaking them down, and they found that for example, water, when you took a water molecule and you broke it down, you got these definite proportions between hydrogen and oxygen. You always had, you know, more hydrogen. You had two hydrogens for every oxygen, and they did this with a lot of different compounds and started to see, hey, maybe we have these atoms of matter, and because of these definite proportions that you find in certain things. Carbon dioxide, you know, you get 2 oxygens for every carbon, things like that. And this is when people started building that thing over there, the periodic table of the elements. Okay, periodic table of the elements is basically a big old poster that shows you the atoms, you know, those things that are no longer indivisible. Brownian motion was another piece of evidence that kind of gave credence to the idea of atoms. And basically there was a scientist whose name was Brown, and he noticed that in containers with water in them and little pollen grains floating on the surface, if the water was totally still, there was no wind, no waves, and no nothing, he noticed those pollen grains would move around, they kind of bounce around randomly. And his theory was, hey, there must be atoms of water that are moving, hitting those pollen grains and making them bounce around. And so it was another piece of evidence that potentially led to the idea of the atomic theory. So just to give you a little bit of an idea of what we're talking about with size, I think it's really hard to grasp how small atoms really are. We know they're small. We know they're really small, but what does that mean? Well, the radius of an atom is roughly 10 to the negative 10th meters. That has a special name. It's called an angstrom. Okay, sometimes just abbreviated with a capital A and a little circle on the top. That pen's not working so well. Can you guys see that okay? That pen would be better. And the nucleus of the atom, which we'll talk more about how we know there's a nucleus and how we understand atomic structure, but the nucleus of the atom is on the order of around 10 to the negative 15th meters. So we're looking at, you know, 100,000 times smaller than the atom itself. You get down into the nucleus. Again, what does that mean to us? Again, those are distances and sizes that I can't really fathom. So Here's a decent analogy. If you think of the atoms in your body, there's the same number of atoms in your body as you could fit people inside the sun. Okay? Approximately. And even that for me is really hard to grasp because the sun's like so big, I can't imagine that. But kind of atom, person, star, that's kind of a good analogy. Another one that's maybe a little bit more attainable is kind of the atom, apple, earth analogy. The number of atoms in an apple is approximately the number of apples you could fit in the earth. Okay? So, yeah. Okay? Yeah. That gives you a rough idea of the size of atoms on average. Now here's kind of a cool thing to consider. Think about language for a second, at least the English language. How many letters do we have? 26. With those 26 symbols, we can communicate everything that we can communicate, which is pretty amazing if you think about it. It takes 26 symbols to do everything that we do in terms of verbal and written communication. Okay? In terms of stuff, if you think of everything you can think of that exists out there, it's basically made up of about 100 elements. Everything you can think of, from gummy bears to anything else you can think of, okay, is made up of 100 elements, and that's what this periodic table over here is, okay? You look at this table, and you get the ones that are written in black are the elements that can be found normally here on Earth. The ones, when you start getting into 111 and 112, these are elements that have been created in a laboratory and generally don't survive very long. They're not naturally occurring. So, anything you can pretty much conceive of is created by about 100 types of atoms, which is kind of cool. You put those all together and form molecules, then you start getting myriad things. And that's kind of like if you think about letters, we have 26 letters, and individually you put them together and you can make an infinite number of words, and from those words you can make paragraphs and communicate all sorts of things. Same thing holds true with atoms and stuff, kind of. Yeah. Okay. Let's talk about moles. This is chemistry. If you guys all took chemistry, right, this is just kind of chemistry review. I know it's physics, but we're doing a little review chemistry. Remember that the idea of a mole is just a number. It's just a convenient number when we're talking about really small things. It's kind of like a dozen is just a number. We deal with eggs by the dozen. I don't know why. That's just what we've chosen to do. We deal with atoms by the mole because it's kind of a convenient number for us, okay? It turns out that a mole is 6.02 times 10 to the 23rd things per mole, right? If I had a mole of dollars, I'd be a happy, happy guy, right? That's just a lot of stuff. When we talk about atomic mass or molecular mass, that number is the number of grams of stuff you would have if you had a mole of that molecule or that atom, all right? So if I go over here to the periodic table and I look up oxygen, it has an atomic mass of 16. 15.9994 if we want to be super precise, but let's just call it 16 for now. So the atomic mass of oxygen is 16. What that means is if I have a mole of oxygen atoms, if I have 6.02 times 10 to the 23rd oxygen atoms, it will have a mass of 16 grams, okay? So we're going to use this a lot in this unit where you have to figure out how many atoms you have and stuff if you have a certain amount of mass. And I know in chemistry you learned a way to do this, and I usually just do it by thinking about the units and doing, what's that called? They called it in physics, where you had, or in chemistry, where you had the units and you cross them out and multiply. Yeah, there's factor. Ooh. So again, a lot of this is going to overlap with what you guys did in chemistry. Hopefully that will be very, very helpful. But let's talk about states of matter. And in general, we think of material existing in 3 states or 3 phases: solids, liquids, and gases. There is also a plasma phase, which we'll touch on. But really in this unit, we're going to mostly talk about solids, liquids, and gases. And what IB wants you to start doing is thinking about these things on a macroscopic and a microscopic scale. You guys know the difference between those 2 words?
Big, small.
Big and small. Macro, big. Micro, small. So when you think about a solid, let's just talk about it for a second in terms of the macroscopic scale. Can anybody differentiate between solid, liquid, and gas macroscopically? How do you determine one from the other?
One is the other one.
Okay. So let's just stay macroscopic for now. So solids are hard.
Liquids are brittle.
Okay, excellent. So let's think about a container. Let's say on a macroscopic scale, if I put a liquid in a container, what will it do?
Form the container.
It'll form to the container, but will it fill it entirely? Unless I fill it up entirely, right? But if I put a gas in the container, what will it do? Fill the space everywhere. And a solid just holds its own shape, right? Those are kind of macroscopic definitions of those things. But let's think about them more on a microscopic scale. What's the difference? Because let's say water is kind of the classic example. If I have solid water, liquid water, and gaseous water, on an atomic level, I still have water molecules. Okay. So let's think about them in terms of energy now, because that's what we talk about in physics is energy. What's the difference between solid, liquid, and gas molecules on an energy level? They have more energy. Excellent. And they're moving very fast. Excellent. And how about the relationship to one another? And a gas, are they interacting? Are they? No. There's more space. They do interact by colliding, okay? But they just bounce off. They don't glob together because they have so much energy. Yeah? So then we take away some of that energy. They move slower and slower and slower. What do? They stick together and become a liquid. But they're still fairly energetic. So they're not forming like what we call a crystal lattice. They're not, or like they're not forming tight bonds. They can still flow past one another, but there is a connection. Yeah? They do pass and around and move around one another. So some of the molecules are bound together, but there's also an ability to kind of move past one another. If I remove even more energy, they move more slowly. And what kind of energy are we talking about, by the way? And wait, what? Kinetic, there's an intimate relationship between kinetic energy and heat. So good. If I remove even more energy from the liquid, what do those molecules do?
Solid.
They form a solid. They form bonds. They bond together and form a solid. Okay, so that's kind of basically the difference between solid, liquid, and gas is the amount of energy the atoms or molecules have, and therefore how connected they are to one another. Yeah? Excellent. Temperature. We talk about temperature all the time. You probably think about it, is it cold today? Is it hot today? In a real basic, gross sense, what is temperature? This is really stupid. Just like in general, what is temperature?
How hot things are.
Yeah, you guys are good. That's what I like to see. Good. Don't overthink it. It's basically how hot or how cold something is, okay? But we obviously want to go a little bit deeper than that. From a physics definition, what do you think temperature is measuring?
Vibration.
Vibration. And from a what would we call vibrations? What kind of energy?
Friction.
Kinetic energy. Excellent. So temperature is measuring the kinetic energy of the molecules of something. Now let's say I measure the temperature in this room. There's a bunch of molecules bouncing around. Do they all have the same kinetic energy? No. So what do you think temperature really is measuring? Awesome. Average kinetic energy, okay? This is a definition that you will see again. This is part of your IB syllabus. Be sure you can define temperature. It's a measure of the average kinetic energy of the molecules of something. Is it actually the average kinetic energy of those molecules? What units do we measure temperature in? Celsius, Fahrenheit. If it was actually the average kinetic energy, what would we measure temperature in? No, well, that's that energy. What's the unit for energy? Joules. So we would say, oh, the temperature is 4,000 joules today. But we don't do that, okay? So that's why it's a measure of it. It's not actually the energy. It's a way of kind of giving the energy a numerical value, all right? And we have 3 different scales that we do it with. Am I going to talk about that yet? Nah, not really. But what are those 3 scales? There's the temperature scales. What are the 3 main temperature scales that we? Celsius, Fahrenheit, Kelvin. Beautiful. In science, Kelvin's going to be the way we go, generally speaking. But Fahrenheit and Celsius are equally valid. They just have different starting and ending points. What temperature tells you is the direction that energy will flow. Okay? If I put 2 objects in thermal contact with one another, energy will always flow from the hotter object to the cooler object, from higher temperature to lower temperature. A couple of questions for you to think about. Question: which has a higher temperature? Okay, a cup of boiling water or a pot of boiling water? Which has a higher temperature? Oh, excellent, Renee. It is the same. How do you know? Because as long as they're at the same elevation and the same pressure, they will boil at the same temperature. Beautiful. But Hayden, what were you saying?
Well, I mean, one has more stuff than the other.
More energy. Which has more energy?
The pot.
The pot. But they have the same temperature. Okay, that's the difference between temperature and heat. Okay, temperature is the average kinetic energy of all the molecules, and a cup or a pot, if they're both boiling, they'll have, if they're at the same temperature, they'll all on average have the same energy. But if you have a pot of boiling water, you have more molecules, therefore you have more energy overall, so you have more heat.
So
Okay?
the amount of energy.
Exactly. So,
I don't know. I still see it as a-
so temperature is just a measurement of what the average energy of the molecules is, whereas heat is the total energy of that material.
Okay.
All right? So the pot of boiling water would have more energy than the cup, even though they're at the same temperature. So one of the things that happens with most materials is most materials change with heating or cooling. You know, the more thermal energy they have, properties tend to change. And one common change is expansion. Most materials will expand the hotter they get. Water is an exception of this. From 0 to 4 degrees Celsius, it actually contracts, which is kind of weird, but it's one of the reasons why ice floats. And if you think about it, most solids will not float in their liquid form. Most solids, if you put it in its liquid form, the solid would sink, right? Because it's usually more dense. But ice doesn't do that, and it's an unusual property of water. It's actually probably one of the reasons why we have life on Earth. We can get into that discussion more later, but just kind of think about that for a second. Think about, lakes when they freeze in the wintertime, they don't freeze solid because and the fishies can live underneath. But if ice was more dense than water, bodies of water would freeze solid every winter, and it would be different. Things would change.
0 to 4 degrees Celsius.
Here are some other properties of things that change with heating. Electrical resistance. You guys know that, remember from our electricity discussions last year. When wires heat up, what happens to their resistance?
Goes down.
Oh, it goes one or the other. Which way?
Down. It goes down. Less resistance.
Resistance goes up with heating. Okay, tends to go up with heating. All right, and that's generally true. The color that an object radiates will change with heating. Think about like blue flame versus yellow flame versus white flame. We talk about blue flames are hotter than yellow flames. Well, that has to do with the temperature of that flame or the temperature of the object that's radiating it. Or have you ever?
Green flames.
Yeah. So we know that as things get hotter or colder, their properties change, and we can use that to make a device to measure temperature. What do we call the device that measures temperature? Thermometer, a thermometer, right? Right? A thermometer. It measures thermal energy. And basically, this is how we make thermometers. The idea that things expand or contract, that's your traditional thermometer, right? Remember, you got a little glass tube, you put some alcohol or some mercury in there, and as it gets hotter, that alcohol or mercury expands. The glass also expands, but fortunately, the mercury expands more, and it goes up or down the tube, and you can make marks on it and say, ooh, it's a thermometer, okay? Bimetallic strips can be thermometers. We talked about them a little bit last year with electricity, but remember, if I take two different kinds of metal and glob them together, and as they heat up, one expands more than the other, and the metal will curve. You guys remember that? We talked about that with like circuit breakers a little bit. Yeah. You can make a thermometer that way too. The more it curves, the more heating has happened, and you can make a scale and just measure a thermometer that way. Turns out a lot of newer thermometers deal with this electrical resistance concept, and there's a name for them. So if we're going to measure the temperature of something, we need a scale, a temperature scale. And we've already talked about the three that we use. And generally, all a temperature scale is someone came along and said, hey, let's pick two reference points. And our general reference points, for some reason in our culture, we like the freezing point of water and the boiling point of water. We pick those kind of as our reference points. And then you have to decide how many pieces in between you're going to have, how finely you're going to divide up between those 2 points. And that's kind of what we did. So what are the three scales again? Fahrenheit, Celsius, and Kelvin. On the Celsius scale, hey Colt, on the Celsius scale, what is the freezing point and the boiling point of water? 0 and 100. Beautiful. So someone decided, I'm going to make 0 freezing, I'm going to make 100 boiling, and I'm going to break it up into 100 pieces. And that was Mr. Celsius. And he was a pretty smart guy. Okay? Yeah, I know. Someone else, Mr. Fahrenheit, he comes along and says, no. Actually, I think he might have been first. I don't know. I don't know my history. But he says, freezing point of water, I will make it 32. And he, in fact, didn't choose the boiling point of water. He chose body temperature. And he stuck the thermometer under his armpit to measure his body temperature or whatever, and he said, I will make body temperature 100 degrees. Boom. And I'll break it all up in between. And it turns out when you do that, where do you find the boiling point of water? 212. Okay? So boom, he's got a different scale. Lord Kelvin comes along and says, all this other stuff's happening with gas laws that we'll study. And it turns out on the Kelvin scale, where's the freezing point of water? Anyone? Yeah. 273 Kelvin. And the boiling point of water, 373 Kelvin. Okay? So those are our three main scales. Celsius, Fahrenheit, and Kelvin. You will need to know how to convert mostly from Celsius to Kelvin and back and forth. Fahrenheit we really won't deal with very much, but you will get questions where it says 32 degrees Celsius, how many Kelvin is that? So let's try it. 32 degrees Celsius, how many Kelvin is that?
0. Oh, sorry.
32 Celsius.
32 Celsius?
32 Celsius,
Oh, wait.
how many Kelvin?
Oh.
Notice, well, first of all, okay, let me backtrack for a second. How does the size of a Celsius, how does the size of a Celsius degree compare to the size of a Kelvin degree? They're the same. They're the same. So what's 273 plus 32? 305. Okay, that's how you do it. All right. Let's look at a quick question here. So let's say I have a glass thermometer filled with mercury, which they don't do so much anymore because it's kind of dangerous. But if the glass expanded more than the mercury as the thermometer were heated, what would my thermometer do?
It goes down as it gets hotter.
So 0 would be on the top and 100 would be at the bottom, right? Because as it heated up, the column would get shorter. You know what I mean? Something to think about. You guys are good, okay?
That's cool.
Yeah, it'd be upside down. La da 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 da. Okay? We just talked about this. So which of the two, Celsius or Fahrenheit, has the smallest degrees? Fahrenheit. And therefore it's a more precise tool. Actually, if you're measuring to the nearest degree, Fahrenheit measurement is a more precise measurement than a Celsius measurement because, Celsius degrees are almost twice the size. All right? Let's explain the difference between heat and temperature. Who would like to go with that one? Taylor.
Well, it's a measure of how, with the molecules, and you give more energy, you have more molecules, you have more energy.
Okay.
And temperature measures the average kinetic energy.
Okay.
So that can be the same.
They can be the same, but the heat doesn't have to be the same. Excellent. And heat is generally what flows. We're going to talk about heat being transferred between objects. Temperature doesn't flow. Temperature determines the direction heat will flow. But heat is the thing that flows, and heat is just energy. All right? Okay, good. So there's that. We've got about 2 more minutes. These are all just kind of review questions at this point. Triple point of water is 273.16 Kelvin. What is that on the Celsius scale?
What is it?
What is that on the Celsius? What is it? 0. It's actually 0. Okay. 0 Celsius. It's the temperature at which water, any material, but in this case water, can exist as both a solid, liquid, and a gas. Technically it's 0. Technically 273.16 Kelvin is 0 Celsius, but we usually forget about the 0.16. Okay, good. What are the freezing and boiling points of water on the Kelvin scale? Oh, look, there they are. Get the answer. Okay, good. You guys need to know this stuff. All right. Define absolute zero. We haven't even talked about, heck, absolute zero. But what is absolute zero, Robbie? Sorry, he had his hand up first, Carson. I know.
Absolute zero is the point where molecules stop moving.
Okay.
And we can almost get there with a machine. That's
Yeah,
simulated,
yeah.
If the machines break down.
Because remember, excellent. Temperature is a measurement of the average kinetic energy, which is motion. So theoretically, there should be a temperature at which motion would stop, right? We call that temperature absolute zero. What is it on the Kelvin scale? 0. And please understand this. Absolute zero is absolute. There are no negative Kelvin temperatures. It would be physically impossible, okay? Just like the speed of light is absolute. Now, I know we say, like, you go down the highway and there's a 55-mile-an-hour speed limit, and you guys go, well, that's not absolute. I'm going to go 65, right? You can't go negative on the Kelvin scale, and you can't go faster than the speed of light. There are certain things in the world, in the universe, that are absolute, and temperature is one of them. Okay? That's why we call it absolute zero.
Is it absolute zero in space?
No, but it's very, very close. Well, no. It's like 3 Kelvin. 2.7 Kelvin is kind of the average temperature of the universe when you're out there.
Place where it's absolute zero.
Thank y'all for listening. I'll see you tomorrow.